Thank you everyone for coming. There's a lot more people here than I expected, so I kind of want to run away, but I also realized that I'm the last thing standing between you and a nice dinner, so I'm extra grateful that you've come here. The title of today's session is Lost and Found in Translation, and we're going to be talking a bit about a journey into building decompilers using machine learning. If you don't know what a decompiler is, don't worry, because I don't either. When I was researching this talk, I tried to dive into the Git code base, but I was very quickly overwhelmed. But it's okay, we will discuss this later. But more than just kind of building decompilers, I also want to talk a bit about a journey into how ML models are built and what that kind of means for security and maybe for us as technologists also in a kind of broader sense. So who am I? I'm Camilla, and I currently work at Storytel, the audiobooks app, building ML systems. And before that, I spent a few years at Elastic in the machine learning group, where I was researching how we can apply machine learning methods to create various solutions for security problems, such as detecting malicious activity in DNS traffic. So I learned lots of lessons there about what works and what doesn't, and kind of where the hype is and where it isn't. And also, this is what stable diffusion thinks I look like, and I think it's pretty accurate before my first coffee and when I'm trying to install something that doesn't work. Okay, so the kind of agenda for today is going to be a bit of a mix, so I don't know, don't expect like miracles to rain from the sky, but I thought that we would start with a kind of 1,000 feet overview of what's happening in the machine learning world today. And more, it's kind of starting to spill into the world of everyday people as well. And if you, like me, have been on Twitter, and you've probably seen all the hot takes about how ChatGPT is going to like cook your breakfast for you and do everything else. So like we're going to start by talking about that. But then after that, I want to kind of deep dive into the details and just show you how, in general, you would start applying machine learning to solve your security problems, what kinds of things you should think about, and kind of how the mechanics works, but kind of on a very high level, so you get an intuition, but don't get bogged down in the details. And then finally, we're going to get into the meat of the presentation, which is trying to build a decompiler using machine learning, and we're going to ask questions such as, can we do it? Should we do it? Why should we maybe not do it? And we're going to take a look at some attempts to see what people have done and kind of see what works and what doesn't work. Okay, but let's start with the fact that probably all of you and I as well have had to already go into our Twitter settings and just freaking mute the word ChatGPT because you can't take it anymore. When people are every day telling you how ChatGPT is going to replace Google and how it wrote this great haiku and it told you what to have for breakfast and what to read to your kid. And like, don't get me wrong, it is really impressive what they have achieved, but it also kind of highlights maybe a broader problem in my field of technology, machine learning, which is that more and more technologists are looking at the clouds and kind of seeing faces there. So seeing patterns and maybe human-like behavior where there really is none. And more concretely, what I'm kind of talking about is an incident that happened in the summer, and you maybe heard of it as well. It was a Google whistleblower, a software engineer working in the machine learning team, who kind of claimed that the AI chatbot that he was interacting with had the consciousness and the capacity of, I think it was an 8-year-old or a 6-year-old child, and he was kind of trying to hire a lawyer to assert personhood for this chatbot. And this kind of made big news all over the world because he was fired very quickly. And it kind of sparked a conversation about, like, first of all, what is a person? Who gets to decide what is a person? That's like a talk for another time for sure. But also that are we as technologists kind of looking at these systems and we're just so impressed that we can't really see the forest for the trees, and we're just kind of imagining things that are there when it's really just a very sophisticated statistical mechanism. But yeah, as I said, that's kind of that's a topic for another time. But more closer to security, I think we can take a look at this use case. So at least as long as I've been coding, just a bit of less than a decade, there has been this phenomenon of copy-pasting from Stack Overflow. I'm sure everyone here has probably done it once or twice. I know I have. But now we kind of have that, but taken to another level, which is Copilot, GitHub's new code generation program. I don't know how many of you here write code every day, but at least in the software developer circles, GitHub Copilot is like a new extension that you add to your favorite editor, such as Visual Code, and then it helps you write code. And sometimes you can like write a comment and it will just auto-complete the whole function for you. And this technology is built by OpenAI, and it's kind of based on the huge public data sets that are hosted on GitHub. But there isn't much information about how it actually works. Now, of course, in my field, there is this age-old wisdom that if you put garbage into something, then you will also get garbage out. So if we're thinking about the impact of large language models on security, and we're thinking about the case of Copilot, we might ask, okay, there's probably a lot of vulnerabilities in this free code that's hosted on GitHub. No one has been taking a look at that. So is it reasonable to assume that, well, we put vulnerabilities into this model, so it's probably quite likely that when people are using this to generate code for their own projects, that they would write code that's kind of weak or susceptible to attack. So this is probably definitely the case, and the kind of sad part about my field, in a way, is that when you're building a machine learning model, a lot depends on the training data and the quality of the training data, sometimes even more than like the construction or the architecture of your model. But this is also, like, the data cleanup and understanding is also the, like, least desired part of my job as an ML engineer and as a data scientist, in that no one wants to kind of invest time into cleaning data and curating data and assessing the data, because it's not very exciting, and usually the tooling is not there. So as I said, these large machine learning models like Copilot are trained on a lot of public code, and probably no one has kind of taken the time to really take a look at it. So there is definitely a danger that we are putting vulnerabilities into these large language models, and then we're kind of automating Stack Overflow copy-paste, but on a much larger level. But what makes this really kind of dangerous is that a lot of these answers look very convincing. And sometimes we even kind of develop a blindness. We say, okay, well, computer says so, so I trust the computer more than I trust myself. And in fact, this kind of led to the incident. I think this happened a few weeks ago, right as soon as ChatGPT became live, in that Stack Overflow temporarily banned answers from ChatGPT. I'm not exactly sure how they were detecting it, but they banned them because a lot of the answers were almost correct, but then not exactly. And the deceptive part was that because they're written in a very fluent language, then it's kind of hard to tell that they're not correct unless you're a domain expert in that particular question. And there has also been a lot of interest from the academic security research side about quantifying exactly how many vulnerabilities large models like Copilot are introducing into code bases. And this is a quote from a paper that was recently published that says that, for sure, given the vast quantity of unvetted code that has been put into Copilot, that there will be a high probability that the language model will have learned from exploitable buggy code. And then this paper that was published by Hammond Pierce and collaborators kind of goes on to really quantify how often does Copilot generate code that's, for example, susceptible to some kind of memory bugs or other kinds of things. And what they do is they take 25 risky scenarios as defined by MITRE, and they kind of craft prompts for Copilot around those scenarios, and then they let Copilot generate various kinds of code snippets for those scenarios and assess how many of the completions are weak or vulnerable to a certain kind of attack. And in some cases, it's as high as 40%. So it certainly will be kind of an issue in the future for those of you who are working in, say, teaching developers how to assess whether their code is secure or how to write secure code. You will probably have to deal with output that has been generated by Copilot in some form or another. But then for us, on working on the other side, on the red team side, you might ask, okay, well, we have this massive machinery that has ingested tons of text, and it's unintentionally automating vulnerability generation. So what if we could take advantage of that in a evil or not so evil sense? And there have been a lot of proofs of concept sort of posted on Twitter, where people are trying to either get ChatGPT to generate an exploit snippet or explain how to exploit some piece of code. This, of course, is kind of a very simple example. It's just a cross-site scripting vulnerability, but I've also seen a few other ones that are more advanced. So there is also kind of this fun gem that's coming for those on the defensive side, is that now we can kind of automate vulnerability creation on a much larger scale than before. All right, so that was kind of a 10-foot overview of what's happening with large language models, and we'll touch upon how they're constructed in the last part of the talk, where we're trying to build the decompiler. But for now, I kind of want to take us on another journey, which is to show you how you take a problem, whether in security or somewhere else, and how you start to think about applying machine learning to solve it. And this is going to be on a very conceptual level. So how do we harness machine learning for good and evil? What does the process look like for designing a machine learning solution? And more importantly, it's kind of important to realize that not every problem is a good candidate for a machine learning solution. And sometimes it's really hard to separate the kind of hype from the real gems. And I, for example, know that in the security domain, there are lots of companies that are trying to make AI solutions. There are lots of open source solutions that use ML for automating various defensive or offensive security solutions to security problems. But sometimes ML is not a good hammer to hit this nail with. And I think it's important for yourself to develop some kind of intuition about when a machine learning model would be a good solution and when it simply is not. Okay. But in order for us to develop an intuition about how to solve security problems with machine learning, we first have to take a brief look at the 3 different families of machine learning models that are kind of currently being actively researched. So the first family is supervised learning models, and these are models that you train with labeled training data. So you can, for example, think of an anti-malware or an antivirus device that's being trained on lots of labeled examples of malicious and benign binaries, and then it's kind of producing a model that can detect future samples. The other family is unsupervised learning. This is for cases where you want to discover patterns in data, but you don't have, for example, any labeled training data sets. You just say want to cluster some data points to detect outliers, for example, or things like that. And then finally, we have reinforcement learning, which is mostly used in gaming, say to develop autonomous agents in games, robotics, and also increasingly in combination with supervised learning, reinforcement learning is used to generate large language models. So for example, ChatGPT has actually been built on a kind of combination of supervised learning and reinforcement learning, where it is able to learn from the instances when it doesn't produce a good answer, and it's kind of able to improve over and over. Okay, so those were the kind of 3 broad families of machine learning models that you can use to solve your problems. But the kind of most simple one to understand, I think, in a conceptual level and applicable to this setting is supervised learning. So we're going to go with that for now. So let's say we want to build a toy malware classifier. This is a classic example of a supervised machine learning problem. So we have a training data set. Say we've gotten some goodies from VirusTotal, and we've maybe rated some Windows binaries. So we have a 2-class training data set of our malicious binaries from VirusTotal, and then we have some benign binaries that we know are benign, at least hopefully. So what's our goal here? So our goal can be broken down into 3 steps. So first, we collect our data set. Okay, we have that. Then we build a model, and we're going to take a look in a moment at what exactly do we mean by a model, because I know that's kind of an abstract concept, and people are throwing around all these terms like this is a 100 million trillion parameter model, and this is a 2 billion parameter model, and like it's kind of hard to really grasp like what's going on. And then finally, we're going to use that model to predict if a new binary that, let's say, has just been come up on our radar as an alert, whether that's malicious or not. Okay, so as promised, I was going to tell you a little bit about how to start thinking whether a problem is a good target for a machine learning solution. And I think there are kind of like two rules of thumb that you can keep in mind. So first of all, a problem is a good target for a machine learning solution if the data involved kind of evolves quickly. And I think if you think about malware detection or malware classification, you can kind of figure out that it is really true. Like there are hundreds of millions, probably, of new malware variants that are coming out each year. So it will be really hard for a rule-based approach to keep up with this, especially if someone is handcrafting the rules. And then the second rule of thumb is that the problem involves large amount of data or samples that have to be analyzed on a daily basis, so that it would pretty much be intractable for a human to ever go through all of that. And like detecting malicious traffic in DNS logs, for example, is a classic example of this. In any large or mid-sized organization, there would be so many DNS queries per day that would pretty much be impossible for anyone to kind of sift through that to see if there is any like DGA activity going on there or anything else. And I think the same applies to malware as well. There's lots of new variants coming up every day. It's hard to keep up with rule-based approaches, and it would be hard for analysts to kind of scale their workflow so that they would deal with the large amount of malware samples that they would have to analyze daily. So how would this then actually work in practice? So unfortunately, machine learning models can't understand binaries in the same way like a disassembler or a decompiler would. So they're basically sequences of mathematical operations and matrix multiplication. So they can only operate on numbers or vectors. So that is why the first step in any machine learning project is feature engineering. So what this means is we take our malware binary or our benign binary and we try to figure out what would be the interesting features that could be calculated from it so that we could pass them on into our model. And this is where kind of the science in machine learning becomes more of an art, because it's not always immediately obvious which features you should compute for which problems, and there is no like universal set of features that would be a good solution to any problem. So some examples that you would potentially compute if you were trying to build a model to detect malware would be like the average length of strings in the malware, the presence of certain keywords that are known to be associated with malicious activity, its length in bytes, some libraries that it imports, and so forth. And at the end of this feature engineering procedure, what you have is a sequence of numbers for each of these, and they kind of become what we call a feature vector. So you repeat this procedure for your benign examples, these blue ones, and then your malicious examples, these red ones. You process them both in the same way, and you get these numerical vectors out of them. And what that essentially means is that now you've kind of taken these binaries and you've projected them into a multidimensional mathematical space. So for simplicity, I've just put 2 dimensions here, but you can imagine that these vectors can have hundreds of dimensions. And so basically now your malware and your benign binaries are kind of blobs in this multidimensional space. And now we kind of get to the exciting thing, which is how do we take this space and how do we create a model out of it? So we come to the question of like, what really is a model? Like when we've transformed the problem of malware classification into this kind of mathematical space, what does it mean to create a model when we're talking about it in these terms? And it's as simple as like slapping a line or a plane into the space so that it somehow separates these two classes. So that's what we call a decision boundary. And like this is the world's worst classifier because I just literally slapped it on there. It's the world's worst model, but this could be a random model. So what this model tells us that everything that falls on the right side of this space is malicious, and everything that falls on the other side of the line is benign. So there you go. We've successfully created our first very poor machine learning model, but there it is. Now, of course, we want to be able to use this model to classify when we get a new binary, whether it's a malware or not, because we might want to do something about it if it's malicious. So how do we do that? Well, we take this new incoming binary sample, we put it through our feature engineering pipeline, because as you remember, you have to somehow transform the binary into a numerical vector before the model can understand how to deal with it. And then you see on which side of the boundary does it fall. And in this case, it would fall on this lower side of the boundary, so the model says that it is malicious. Now, of course, this model is really poor because, as we already see, just on the training data where we know the ground truth, so we know which of these are malware and which of these are benign, we can already see that because the line bisects the space, on this side, some of the malicious examples actually fall on the side of the benign class. So it's not a very good model at all, but this is basically a model. Now, how do we actually improve on this very poor choice of decision boundary and make it fit our data better? Well, the crux of this is to make the line be more flexible so that it can actually model the patterns in our data, and with that, hopefully be able to give us more accurate predictions in the future. So our goal is to start with something simple and kind of make the model more flexible, make the line more squiggly so that it better captures the patterns in our training data. And this is kind of all there is to it in a very, very simple nutshell. Now, of course, I'm glossing over a ton of details about what happens, but basically, there we have it. So how does it actually look like when we're at the machine learning model gym and the model is training to see what weights it should assign so that it can model the data better? Well, we kind of have these training loops, and at each iteration of the loop, we evaluate how the model is doing currently on the training data. So at stage 0 here, we have our poorly chosen line. We can kind of see that a lot of these malicious samples fall on the wrong line of the decision boundary, meaning that they're misclassified as a benign when they shouldn't be. So we can kind of quantify how many of our training data points the model gets wrong, and then we can adjust the model during the next iteration slightly by moving the line up and down, and then recalculating to see if it improves or not. And we do this process many, many times until we get to a stage where we say, okay, this is kind of an acceptable model. It only gets one data point in the training data wrong, so I can kind of probably live with this. But then you can also ask, like, okay, in this case, we decided that our model would be a straight line, but what if that's a bit too rigid? Like, it can't really wiggle around the data points in this mathematical space and capture patterns in the data. So this is where we come to the other kind of art, not a science part of machine learning, is being able to select the model correctly. So maybe that line model that we used was too rigid. Maybe we need some kind of squiggly line, and when we train it, it gradually learns to model the patterns of the data in such a way that it's a little bit better. Or maybe not, or maybe the straight line was kind of good enough for our use case. So how do we go about choosing a model? And the kind of scary answer is that there is this concept of no free lunch in the machine learning world. And that means that there isn't a single model that we know out of the box will be the best solution for every single machine learning problem. So this is kind of where the art part comes in, and the experimentation is that you simply have to, you develop an intuition, but you also have to try a bunch of different solutions before you come to one that fits your data and your problem. And just to illustrate, this is from a very famous machine learning package called scikit-learn. They've done this illustration to show you what are the different kinds of decision boundaries that various models learn. And here on this side, we have the data set. So you can imagine that for our classification case, these red points could be the malicious malware binaries, and these blue points could be the benign ones. And that's how the data set looks like when we project it into the mathematical space after extracting our features. And as you can see, there are some classifiers that learn very rigid decision boundaries, so that even a small change in the parameters would immediately kind of cause the class label to go from malicious to benign or vice versa. And there are other classifiers that learn kind of very smooth, very rounded decision boundaries. So there is kind of like a lot of choice, and it's not always very clear at the start of the project what is the thing that you should kind of use. So that was a brief tour of how you might take a problem in security, say malware classification, and how you could start thinking about it in terms of machine learning and also building a model out of it. But getting back to what we're here for, which is to try and kind of take the knowledge that we've just built upon in the first part of the presentation and seeing if it's possible to build a decompiler using some kind of machine learning model. So can we do it? Should we do it? Why is this a bad idea? Okay, so what is decompilation? So decompilation, if you've ever reverse engineered a malware sample or a binary, you probably know that the output that you get from the disassembler is a bunch of assembly code. And it is possible to definitely read and understand what's going on there, but it usually takes some expertise to be able to learn assembly and to kind of understand what's happening on a higher level from the simple CPU instructions that you get. So decompilation is kind of one step up from disassembly, which means that you take a program that's in a low-level representation like assembly, and you attempt to translate it backwards into a higher-level programming language like C, for example. And I'll show you a concrete example. So here is a bunch of assembly code, and this is something that we would get from a disassembler, for example, if we were analyzing a binary. And the goal of the decompiler would be to take this and to give you something like this, so that if you're a malware analyst or a researcher, you could actually see kind of what the code was trying to do without having to go instruction by instruction. So that is the goal here, is to start with assembly and try to recover something that looks like C or Go or whatever, your other favorite programming language. Okay, but you might say, like, why do we need to stick machine learning into this pot of soup as well? Because we already have Hexrays, which is a plugin for IDA, a kind of toolkit for reverse engineering, and we also have Ghidra, which is an open source, I guess, disassembler and decompiler put together that's developed by the NSA, and they already kind of provide these kinds of capabilities. So, like, surely we don't need another crappy machine learning project like messing things up. So yeah, why are some reasons why we might still want to kind of at least attempt? Well, both Hexrays and Ghidra are kind of engineered using rule-based approaches. So they look at the low-level disassembled code and they find certain patterns of instructions that then are known to map to, say, certain higher-level source code functions. And that's kind of part of the way that they help to decompile this code, is that there are handcrafted rules that have taken probably years to develop, which assist in this process. So these rule-based approaches are quite costly to build and maintain. And I think the last time I checked, like, Hexrays has been under development for almost 18 years. So that's a lot of developer time that has been invested in trying to craft these rules. So the second reason why we might want to consider adding machine learning to the mix is that it takes a lot of developer time to create a new decompiler. So I think both Ghidra and Hexrays decompile to C, but say malware authors decide tomorrow that Rust is the language of the day, and like every malware we now see is in Rust. So it would take a lot of developer effort to create a new decompiler that would be able to decompile to another programming language. And finally, the output of decompilers like Ghidra and Hexrays is not really as high-level source code as you would write yourselves. It's more like pseudocode. And what do I mean by that? Well, here we have an example from an academic paper that was also studying this problem, and they say, okay, let's take this function in C, and let's compile it to assembly and then decompile it back with Hexrays to see the difference between the two implementations. So this is what a human developer wrote. And then they compiled it using a compiler into assembly, and then they let Hexrace disassemble it. So if you're an expert, you could probably just like eyeball these two and they would look the same to you. But to me, like, it would definitely take some time to really understand that what's going on in this piece of code is the same as what's going on in this piece of code. So that's what we mean, is that the output of decompilers is kind of more like pseudocode, but it's not really close to what a human developer would write. And also there's this other thing, like when you work in machine learning and all you do every day is you produce machine learning models or hammers for a living, then like everything starts to look like a nail to you. And so here I am sitting and thinking like, well, we know for many years that machine learning models have been able to do natural language translation really reliably. And here is an example from Google Translate that I'm sure you all have used many times. So I'm thinking like, okay, if we know that machine learning models can do this, why can't they just do that? Why can't there be a Google Translate that you put some assembly? It's not really English Google. You have to be a bit better. But yeah, why can't we have a Google Translate that kind of just maps them one to the other like that? So that's kind of how I got interested in this problem and trying to understand if this is even possible. And I'm actually not the first one to ask. This question has been floating around the internet, or if you consider Reddit internet, for at least 7 years. And the idea of being able to automatically generate decompilers goes way back to the 90s, at least. That's where some of the early research papers that were trying to do this. They weren't using neural machine translation techniques or machine learning at all. They were just trying to see if it would be somehow possible to take a compiler and then make a reverse software out of it, but without using machine learning. Anyway, this is not a new idea by any means. It's been floating around various places for a while. However, we have to acknowledge one thing, that when we say, okay, why can't we have a Google Translate that we know works perfectly for Finnish, Swedish, Finnish to Norwegian, Norwegian to Finnish, Swedish to English, why can't we have that for assembly and C? Well, one of the like glaring things that should be staring at you at this point is that code is not natural language. And how can we kind of quantify the extent to which code that humans write is different to the language that humans speak? And one of the ways is just taking a look at the number of words that are in the original sentence and the translated sentence. So here I have one sentence that is in Swedish, and it's direct translation in English. And we can see that when we count the number of words, they're almost the same. So if we would divide it, the ratio would almost be 1. There's 3 words in the Swedish one and 4 words in the English one. However, the same is not true when you compare source code snippets and their corresponding assembly pairs. And actually, there is a research paper that I'm going to circle back to a bit later that really quantified this, like how different are natural language pair translations versus code to assembly translations. And here you can see that when we compare translated sentences between English and German, we see that their word ratios are almost 1. So a word in an English sentence in English has almost the exact same length as its corresponding translation in German. But when we look at various assembly language and high-level source code language pairs, we see that this is not the case at all. For example, when we compare code snippets written in Go and their corresponding assembly snippets, we can see that the assembly snippets are on average 15 times longer than the Go snippets. So there isn't the same kind of information symmetry that you would have in human languages. So that's like warning flag number 1, that this approach will probably be difficult to work. The second approach is that when we translate human language, when we go from Swedish to Finnish or Swedish to Norwegian, there is no compiler in between. So the information that we express in a Swedish sentence, we usually try to preserve it almost equally in the sentence that we're going to write in Norwegian, say. But in code, this is definitely not the case, because in between source code and assembly, what we have is the compiler. And the compiler can do all kinds of things that we as developers probably have little control over, and more than that, have little knowledge of. At least I personally don't know any compiler internal, so I have no idea what's actually happening in this translation step. But for example, the compiler can rearrange the code, add runtime checks that were not in the source code, strip a lot of information, add optimizations, remove code branches that are not going to be reachable during the execution. So there is a lot going on here that is causing this analogy between natural language translation and code to assembly translation to break down. So that should kind of maybe give us a warning sign. This will not be as easy to make work as we think. But let's not give up anyway. Let's take a little bit of a look about how a neural machine translation works for natural language. And then let's see how those similar techniques have been applied to try to build decompilers. And this is kind of where we're going to also touch a little bit upon what makes large language models like ChatGPT work and what was the revolution that happened in the machine learning world in 2017 that enabled all of this to be possible. But back to what I was saying, how does neural machine translation work? Well, it works in a very similar way to how we trained our little toy malware classifier a few slides back. You start with a data set. In this case, it's pairs of sentences or examples in language A and their corresponding translations to language B. So you can already see that there is a little bit of a data collection problem if you're doing this for a natural language, because you actually have to have humans translate this text. But that same problem doesn't exist if you're going to train a decompiler, because you can simply automatically generate a lot of training data for yourself. All right, well, but once we have our data, however we choose to generate that, we do some feature engineering. So we translate we take these sentences and we break them up into words or maybe smaller tokens so that we get a vector representation, a little bit in the same way that we did for our malware binaries, because as I said, these models are essentially doing mathematical calculations and large-scale matrix multiplication, so they can't really deal with words. They have to deal with numerical vectors. And then finally, we train a model that is somehow able to learn that the word for train is this in language A and the word for train is that in language B, and then kind of make it work. So it seems very simple on the surface. However, there's this like little curveball here, is that when you have this kind of sentence in Swedish, I travel from Stockholm to Oslo, you can't simply break it apart and project it into this mathematical space in the same way that we did with our malicious and benign malware examples, because there is a kind of dependency in the way the words are ordered of this sentence. So if you take Stockholm out of the context, then it doesn't really mean anything in this case. You have to have it in that position in the sentence. So that's a little bit of a curveball here when it comes to building language models, is that language is a sequential kind of data structure, and you really have to have the context. You can't just kind of examine words on their own and try to model that. You have to examine the sequence as a whole. And so in order to do that, we have to develop a new type of model. It's not just enough to project these sentences into some mathematical space and then slap on a decision boundary or a line there. We have to develop a new class of solutions. And these are known as sequence-to-sequence models. So as the name implies, they take a sequence of text as an input. They store somehow the context of what the text is saying, where the words appear. They store that in a memory or an internal state, and then they output another sequence, which is the same sentence, but in another language. So this is what's known as an encoder-decoder architecture for neural machine translation, and this is the basis of the state-of-the-art that is currently used in a very advanced form by Google Translate and also by various other large language models. So in this case, we actually kind of have two models. So we have the first model, which is the encoder. You can think of it as this model is the expert in Swedish. So it takes this sequence of Swedish words and it analyzes them one by one while remembering the context. And then it collects all of the information that it got from every word, and it outputs what's known as a context vector. And this vector is then sent to the second part of this model, which is like the expert in English, you might think. So the expert in English takes this context vector that it got from the Swedish expert, and then it's able to, from that vector, to generate the correct sequence of words in English. So if you look at this a little bit closer, what actually happens inside of this encoder and also the decoder to a large extent? Well, at least until 2017, the state of the art for analyzing sequential data were what we call recurrent neural networks. So these are models that are able to keep a certain memory of what tokens or words they have seen before, and then use that to kind of construct a context and understand, if you will, what a sentence is saying. So what happens here? Well, we take this sentence and we break it up into tokens. You can think of it as words, but there are other ways to break up a sentence as well. It's just a little bit beyond the scope of this presentation. So we take the first word, which is I, in Swedish, and then we pass it, it goes into the encoder, and inside the encoder is this recurrent neural network. So we pass the word into that, it analyzes the word, and then it outputs what's known as a hidden state. So this is the kind of memory of what words the recurrent neural network has seen. Then we take the second word, the second token, and we pass it into the encoder, and the recurrent neural network accepts the new word and also the hidden state from the previous step, and that's how it kind of remembers that the word travel is usually comes after the word I. So that's how it, in a very simple nutshell, that is how it builds an understanding, if you will, of what words usually follow each other in a sentence. And if you can imagine that it does this over and over again, millions of times for like hundreds of gigabytes of text, at some point it would develop a pretty accurate probabilistic model of like how it should place words in a sentence so that it actually looks like a human wrote it. So then when it's done processing the first sentence, it collates all of the hidden states into a context vector. And this context is then passed to the decoder, which kind of goes through the same process, but in reverse. So instead of consuming the word tokens, it's taking the hidden state and then emitting the most likely tokens based on the information that it got from there. Okay, so until 2017, this way of architecting language models and of architecting translation models was very inefficient, because if you think back to our process, we have to take each word in the sentence and then kind of process it one by one. So you can't really parallelize this very effectively, which means that training these models can be very slow. But then in 2017, a group of researchers published this paper that is now like probably the most well-known machine learning paper in this language models field, and it was called Attention is All You Need. And it proposed that instead of using a recurrent neural network type of approach, they proposed using a new type of algorithm called attention. And what the revolutionary part of this algorithm is that you didn't have to process each word in the sentence in sequence. Instead, you could do it all in parallel. And this just like blew the door open to training these models on gigabytes and gigabytes of text. And so that's how we got the first, like, the forefather of, or foregrandmother of GPT, or ChatGPT, which is Bert. It's a mouthful to say the actual name. It's bidirectional encoder representations of transformers. I'm not sure how they chose this, maybe because Bert is such a cute name, but anyway. So this was the first model that was trained using this new attention mechanism and this new transformer architecture, and it immediately like blew all of the previous state-of-the-art models like out of the water. It was much better on certain tasks that are used to benchmark this. And the other kind of clever trick that was discovered here was that we didn't need to actually provide a lot of labeled training data for Bert. Instead, what researchers did is they said, okay, you know, the internet is full of text, right? So let me just download, scrape all of that, and then let me create a training data set by simply randomly taking out words from the text and training the model by asking it to predict what the next word could be, and repeating this over and over again until we get to a model that is really writing like almost believably good human-like text, if you will. So what this led to is that now we have a lot more language models than I could ever fit on this slide. But broadly speaking, they can be divided into 3 different families. So there are encoder-only models. These models only have the first part of the encoder-decoder architecture. So they take a sequence of text, like the sentence, I'm traveling to Oslo, and then they project that into some mathematical space. And this is useful, for example, if you just want to take a piece of text and you say want to classify what is the sentiment that's expressed in this text, or what is the topic that is being talked about. The other family, and probably more famous one, is the family of decoder-only models. So these are the models that led to ChatGPT, and these are the models where you kind of give it a prompt, and then it just continues generating the most likely sequence of text that would come after that prompt. So that's basically what GPT is. Stands for Generative Pre-trained Transformer, and that's kind of the basis of most state-of-the-art text generation models today. And then there are, of course, the models that are both encoder and decoder, and these are mostly used for sequence-to-sequence tasks, which brings us back to our original question that we were trying to answer here before we went on this detour, is whether we can use this encoder-decoder architecture to not only translate between pairs of natural languages, but to also translate between source code and assembly. So I did a deep dive into the academic literature to try and see if anyone had actually done like a worthy approach to this. And I found a few papers, not going very far back, because this transformer technology is not very old, so we can't really expect to kind of find papers from the 90s, but there were a few papers that made attempts at using neural networks to decompile assembly code to C. The thing that was a little bit problematic about all of these papers was that a lot of the solutions proposed required a lot of pre-processing of the source code data. So if you remember, if we want to try and construct a decompiler, what we really need is a collection of a lot of source code function snippets and their corresponding assembly snippets. And ideally, you wouldn't have to do a lot of pre-processing, but most of these papers kind of achieved good results by pre-processing the source code data. For example, by generating abstract syntax trees, by doing other pre-processing steps. And to me, this kind of slightly defeated the point of trying to build a machine learning based decompiler, because what we've done just now is we've taken the problem of kind of handcrafting rules or handcrafting different kinds of pattern mappings from traditional decompilers like Ghidra and ML, and we've just reintroduced the same problem back into the machine learning approach. So hopefully there could be something that wouldn't require so much handcrafting, that could be more automated, or maybe this is utopian thinking. But a recent paper that was actually just published at the end of last year does exactly this. So it takes the question of, what if we don't do any pre-processing? What if we just say, you know what, assembly is just some special form of text, and source code is another form of text, and they're just text. And if we treat them as that, and we just use whatever off-the-shelf language model architectures that already exist, how far can we get? Like, how far can we get in trying to actually create a model that takes assembly code and then spits out high-level C code? So they did a really interesting experiment where they basically tried to learn a neural machine translation model to decompile assembly code to C, assembly code to Fortran, assembly code to OCaml, and assembly code to Go. And this is kind of a very, I guess, new development, because I haven't seen decompilers for Fortran, for example, or Go before. So how did they do this? So as mentioned before, they kind of applied the 3-step procedure for generating a machine learning model. So first they constructed the data set, right? So they needed a lot of code snippets that they could compile into assembly. And those would kind of be used as language A and language B in this neural machine translation model, if you will. So they basically scraped a bunch of competitive programming repositories that are public, such as Project Euler. Those code snippets there are usually fairly self-contained and don't have a lot of external library calls, which kind of makes them ideal to study this kind of problem. So that's how they acquired the data. Then they took a very basic encoder-decoder model, very similar to the one I kind of showed on a high level for translating between Swedish and English, and they trained it on this data, just treating both the source code and the assembly code as text. So no special transformations were done. And then they evaluated the result by setting aside a set of source code and assembly code snippets that the model hadn't seen before, then asking the model to take the assembly code, decompile it, and then compare the model's output with what they knew was the correct output. And they measured the edit distance between the prediction and the true source to figure out how many mistakes the model made. So what was the result? So this is an example of what the ground truth is here on the left. So this is the original C function that someone wrote. And then this is what the model predicted from the assembly code that we get when we compile this function on the left. So yeah, it's definitely not like perfect, and there is like the edit distance is quite big. So what they discovered is that on average, almost every other token has to be corrected in some way. But they also wrote that there were some snippets of code where the translation was almost perfect, and then other ones where it wasn't. So for future work, it would be interesting to see what are the snippets of code where the decompilation using neural machine translation is almost perfect. And maybe while we're not there yet where we could have a fully featured commercial machine learning-based decompiler, perhaps we could have like a machine learning-based decompiler assistant that could maybe suggest to you what a potential decompilation is, and then a human who is analyzing this code could then kind of correct it or suggest corrections. So basically, that's where we are in building a machine learning-based decompiler. So we're not there yet, but I think very soon we might have some sort of human-in-the-loop solution. And yeah, OK. You made it to the end. It's 6:30, so congratulations. Most of you are still awake. What did we cover during this presentation? We looked at ChatGPT, why you should be maybe a bit suspicious of things like Copilot, how your job is maybe going to be affected by Copilot. We took a bit of a look at how to build machine learning models, like on a very high-level toy example. And then finally, we looked at whether it's possible to even try and attempt to build a decompiler using machine learning methods, and kind of why it might work and why it might not work. And as we've seen from some research, it kind of does work, though not perfectly, which is maybe what you want your decompiler to do. You don't want to spend your whole time correcting its output. So this is thank you for me. Any questions, comments, or suggestions, you can either ask now, or you can reach me on Twitter or LinkedIn. But yes.
The question is there any work on translating from one language to another directly?
OK, so the question is if there's any machine learning work on transpiling from one high-level source code language to another, and yes, there is. There was a recent Facebook paper that, I don't remember which language pairs they used, but in those cases, I think the performance is much better than in the case of decompiling. So yeah, that work does exist. I'm not sure if it's commercially viable yet, but the research is there. OK. I think we can call it a day. No? Oh, someone else. Sorry. Someone else have a question? No? OK.